Hello everyone. Today we will see what are the different types of problems available in the power system stability. We had already seen power system stability concepts, introduction to power system stability, its classification, and what is swing equation in steady state stability. And in transient stability, we had seen equal area criterion. So, as I had already said in equal area criterion, we can find the solution of swing equation using three methods. They are step-by-step method, modified Euler method, and Runge-Kutta method. Today in this video, we are going to see different problems on swing equation and problems on equal area criteria and step-by-step method, modified Euler method, Runge-Kutta method, problems and formulas related to that. First of all, let us recall the formulas which are needed for solving problems in swing equation. We know this. We know that Ns is equals to 120 F by P. We had already known this. This is the synchronous speed formula. Since we are studying the swing equation for an alternator, alternator will be rotating at the synchronous speed. So Ns is the synchronous speed, which is 120 F by P. We can find this omega, which is equals to 2 pi ns by 60. Then kinetic energy stored Wk, which is equals to half j omega sm square. Then we had H is equals to Wk divided by Sb. And then we had one more formula, M is equals to 2Wk divided by omega Sm. Now this M is equals to 2Wk divided by omega Sm. We know omega Sm can be written as 2 pi F naught. So M is equals to 2Wk divided by 2 pi F naught. This 2 and this 2 gets cancelled to get Wk by pi into F naught. We know that H is equals to Wk divided by Sp. From this we can write that Wk is equal to H into Sp. Wk is equal to H into Sp. So I had substituted this here in this place, Wk. I had taken H into Sp. So we can use M is equals to 2Wk by omega Sm. This is one formula. And M is equals to H into Sb divided by pi F naught. This is another formula. Then we know this. We know that this is the swing equation. This is the swing equation. H by 180 F naught into d squared del by dt square is equal to Pm per unit minus Pe per unit. This is the swing equation. And we know in this derivation of swing equation, we had used this formula. Theta m is equals to omega smt plus del. And this value we should remember, 1 electrical degree is equal to 1 by 6 times of RPM. Now, the swing equation can be also written in terms of, this is the swing equation in terms of H. This is the swing equation in terms of H. We can also write the same, we can also write this swing equation in terms of M also. In terms of H. Now, we will write this swing equation in terms of M. See this, H by 180 F naught d square del by dt square is equal to Pm per unit is Pm actual value divided by base power Sb minus Pe per unit is Pe actual value divided by base power Sb. So I am taking this Sb to the other side. It will become H into Sb divided by 180 F naught into d square del by dt square is equal to Pm minus Pe. If you see this, we had just now derived M in terms of H. That is M is equals to H into Sb divided by pi F naught. So this pi is here 180 degrees. This pi you can take in radian mode. It is pi. In degree mode it is 180. So this total can be replaced as M. So M d square del by dt square is equal to Pm minus Pe. This Pm minus Pe is written as Pa, accelerating power. So this is the another form of representing swing equation. Now, here, if you observe, since m had pi, which is in radians, this del also will be in radians. When we are using this formula, you don't need to worry. This del here represents, here, the del is in electrical degree. It is very, very important. When we are using the first swing equation, that is in terms of H, the del obtained will be in electrical degrees. So you can just convert them into RPM if they had asked. But when you are using swing equation, which is in terms of m, the del obtained will be in radians. So this radians should be converted into electrical radians. This is mechanical radians actually. This is actually mechanical radians. So this mechanical radians should be converted into electrical radians, and electrical radians should be converted into electrical degrees. After converting into electrical degree, you can use the same formula to convert into RPM. So how to convert? We know that del M is equals to 2 by P. Mechanical radian is equal to 2 by P times of electrical radian. I explained this derivation when I am explaining the swing equation. So to understand the relation between mechanical radians and electrical radians, you can refer the swing equation derivation, detailed derivation of swing equation. Now you have converted these mechanical radians into electrical radians. Now after converting this into electrical radians, what we should do? We should convert this electrical radians into electrical degrees. 1 radian is equal to 57.3 degrees. So del in electrical radians is equal to 57.3 del in electrical degrees. So you can write this equation. Here, this is theta m formula. In this theta m formula, this del is directly in electrical radians, electrical degrees, E comma D. So you can convert this into RPM. Now the same theta m formula where this del is derived from this m equation. In this theta m formula, the del is taken from swing equation which has H. So the del is directly electrical degrees. Suppose if H is not given, m is given, then we need to calculate del from the second swing equation where this del is in mechanical radians. So you need to convert that into electrical degrees. So how to convert it into electrical degrees? You just multiply with 2 by P, 57.3 electrical degrees. Then after finding this, you can convert this into RPM if they had asked. Now let us see the first problem. A 2-pole, they had given a 2-pole machine. So P is equals to 2 they had given. And then they had given 50 hertz. Frequency is 50 hertz. This is frequency. This 11 kV. Then this 11 kV is not required for us. Turbo alternator is rated at. So they had given rating. And they had given the power factor also. So this is the SB. Actually, this is power, real power. Since there is megawatt, they had given real power P. You need to convert this into, they had given P. You need to convert this P into SB. How to convert this P into SB? By using this cos factor, we should convert this P into SB. They had given, see, by seeing this unit, you can conclude that it is a megawatt is real power. You should convert this real power into complex power SB by using this power factor. Then what they had given, rotor had moment of inertia of, they had given moment of inertia J. And they had asked us to calculate H and M. So first thing is, as now, just now I had said, first we should find the NS is equals to 120 F by P. They had given F and P, so you got 3000 RPM. Then we can find omega SM. Why? Because all the formulas includes omega SM, not NS. So omega SM is equals to 2 pi NS by 60. We got the omega SM. Now, this is the power. S is equals to, normally, S is equals to P plus JQ. I had explained this many times, but I want to revise once again. P plus JQ, we know that. So this can be written as a complex number can be written as a plus jb can be written as a cos theta plus b sin theta. J b sin theta. So p cos phi p cos phi plus j q sin phi. J q sin phi. So from this, you can find the value of the power, real power. See, S is equals to P cos phi. So what is P? S by cos phi. So you can find actually this you can take it as power. Yes. So MVA by cos phi 100 by 0.5. So this is 200 MVA. Now now we had calculated omega SM. The formula of H, what is H? The formula of H just now we had seen. H is equals to WK by SB, where WK is equals to half J omega SM square. So this is the WK formula. WK is equals to half J omega SM square. You know the value of J, you know the value of omega SM. So you can find the value of WK, and H is equals to this total. This is the WK divided by what is this 200? WK divided by SB. So this is SB. We had calculated here, no? This is SB. So you got the value of H. Similarly, you can find the value of M also. To find the value of M, what is formula? M is equals to 2WK by omega Sn. M is equal to 2WK by omega Sn. We know this omega WK and we know the value of omega Sn. So you can find the value of M also. So this is a small problem in swing equation. Now let us see the next problem. A 4-pole machine, number of poles is equals to 4. This is P. And has a 60 frequency, 60 Hz is the frequency. Has a rating, they had given this is rating, and 0.8 power factor. So you can find this 200 divided by 0.8 will give you the SP. Power factor lagging, moment of inertia of, they had given J, the same problem, similar type of problem. You need to find the value of M1 H. So first step is Ns equals to 120 F by P. You will find the Ns. Then omega Sm is equals to 2 pi Ns by 60. You will get the value of omega Sm. Then Wk is equals to half J omega Sm square. You will get the value of this. Then H is equals to Wk by Sb. M is equals to 2Wk by omega Sm. You can find this. Now the next problem, a 2-pole. This is this is a important problem, which is big problem. A 2-pole machine, number of poles is equals to 2. They had given, and then 60 Hz is the frequency. Having a rating, they had given rating of SB. This is SB, and then power factor. The kinetic energy of the machine at synchronous speed is, they had given kinetic energy. We know kinetic energy is the energy stored, which is Wk. So they had given kinetic energy or Wk. The machine is running at the synchronous speed and delivering 60 megawatt to the load. This power delivered is PM, which is equals to 60 megawatt. Load having a power angle of 8 electrical degrees. This is del naught. Del naught is equals to 8 electrical degrees. The load is suddenly removed. Determine the acceleration. What is acceleration? Acceleration is d square del by dt square. This is the acceleration. So they are asking us to find the acceleration of the rotor. If the acceleration computed for the generator is constant for 12 cycles, determine the value of power angle. del and RPM at the end of this time. So first what we should find? First we should find this d square del by dt square. So I am using d square. To find d square del by dt square, we can use a swing equation. This is the d square del by dt square. No. So to find this d square del by dt square, I should find the h. F naught is already given. PM is already given. PE is not given. So I should find the value of h first. H is equals to WK divided by SB. So what is WK? This is WK, and what is SB? SB is 250 megawatt. This power factor is not required. In the previous problem also, you see here 200 MVA, 0.8 power factor lagging. So we had taken SB is equals to 200 MVA. To find the real power, we can find the magnitude. Real power is equal to S divided by cos phi, but it is not required to find real power, no. So since it is not required to find real power, you can go with the reactive power alone. So no need to find this. No need to use this cos phi 0.8 at all. In this problem also, in the previous problem, I said you just how to find the value. Based on the unit, we should proceed. You see carefully. In this problem, the unit is megawatt. Whenever they give megawatt, you divide with the power factor. Whenever they give megavolt ampere, you directly take this as SB. If they give megavolt ampere, you can directly take this as SB. You can remember like this. When they give megavolt ampere, you can take directly this as SB. When they had given megawatt, you should divide this with 0.5. Here also they had given megavolt ampere. So this 0.8 is not required, and directly you can take this as SB. If megawatt is given, then you divide that megawatt divided by cos phi, power factor. There is one more chance. If they had given megavolt ampere reactive, actually, generally they won't ask, but you should be able to solve when they had given. So if they had given megavolt ampere reactive, then you should divide with sin phi to get the value of yes. Divide with sin phi. Since in this problem they had directly given megavolt ampere, you can take that as SB. So we had substituted SB and they had given the kinetic energy WK. So you will get the value of H. Now this is the swing equation. So from the swing equation, mechanical power they had. Actually here, when you are using this swing equation, this PM is in per unit. So what you should do, you should divide the actual value of mechanical power 60 megawatt divided by base value, that is SB. So you will get the per unit value. And then since the electrical is not given, otherwise they had not given electrical, so you can take this as 0. So you can substitute now. H by 180 F naught into d square del by dt square is equals to 0.24. D square del by dt square is equals to 0.24 into 180 into F naught frequency. Frequency is 60. They had given frequency is 60. So into 60 divided by H. H is 4 point. So as I had explained you in the formulas, whenever you are finding the value of del from this swing equation, from H swing equation, this del obtained will be in electrical degrees. This will be in electrical degrees. So you can see here what we got. Since it is d square del by dt square, this is 600 electrical degrees per second square. This is the acceleration. Now they had asked us to find, we had found out the acceleration. See here, determine the acceleration. Till here we had completed. Now what they had asked, if the acceleration is constant for a period of 12 cycles, this acceleration is constant for 12 cycles. This is first subdivision. The acceleration is constant for 12 cycles. Then what we need to find? Find the value of power angle del, and we should find the value of RPM, that is speed. So we will go to the next subdivision of the problem. We had a formula, time period is equals to 1 by 60 into number of cycles. Actually, the 60 is frequency. So you can tell that time period is equals to 1 by frequency. We know already time period is equals to 1 by frequency for one cycle. Normally, T is equals to 1 by F. We know this already. So for one cycle it is. For many number of cycles, we will just multiply with number of cycles. They had given for 12 cycles. So time period will be 12 by 60, which is 0.2. That is 0.2. Now we know this d square del by dt square is equals to 600. We want this del. So how we will get this del? By integrating 2 times we will get. So if we integrate first time, one differentiative will cancel. D del by dt is equals to 600t we will get. And then if you integrate again, here you are integrating again. If you integrate again, what will happen? This derivative also will cancel and we will get the value of del. So del is equal to 600t square by 2 plus del naught. They had given this del naught as 8 electrical degrees. See here, 8 electrical degrees. So you can take this as 8. Del naught is actually this is 8. Del naught is 8 electrical degrees. And then T value just now we had found out from the given frequency and number of cycles 0.2. You can substitute that. You got 20 electrical degrees. This is the value of del in electrical degrees. Now we know the value of del in electrical degrees. Now we need to find out speed. So we should find out theta m. We should find out this theta m, where theta m is equals to omega smt plus del. If we differentiate this, d theta m by dt is equal to this t. When we differentiate this term with respect to t, we will be having into d by dt of omega sm into t. Here we will take this t. So this t gets cancelled. We will get this plus d del by dt. Now we know that del is equal to 600. D square del by dt square is 600. So d del by dt is equals to 600t. See here. So we can find this. D square del by dt square is equal. D square del by dt square is equals to 600. D del by dt is equals to 600t, where t is 0.2. So we got d del by dt is equals to 120 electrical degree per second. Now we know that 1 electrical degree per second is equals to 1 by 6 RPM. I need to convert this into RPM. Why? Because they had asked the speed in RPM. So we should find in RPM. No. So I am converting this electrical degree per second into RPM. So I got 20 RPM. Now this term I had found out. I had calculated this term, 20 RPM. And what is omega sm? Omega sm is equals to 2 pi ns by 60. Now what is ns? Ns equals to 120 f by p, which is 120 into 60 by 2, 3600 RPM. So we already got this ns in the RPM. Since we are finding in RPM, you can directly add these two things so that you will get 3620 RPM. In this problem, actually, the first we had calculated the value of acceleration, which is d square del by dt square from the swing equation. We had chosen the swing equation, which is having h. So we calculated the value of h. When we choose the swing equation, which is having h, the del we obtain will be electrical degrees. So the acceleration is electrical degree per second square. Then the next subdivision is, they had asked us to find out the power angle and then speed in RPM. So we had calculated the power angle in electrical degrees by integrating the acceleration 2 times. And to find the speed in RPM, what we are doing, we are taking this formula, we are differentiating this, and then we are substituting. This we had calculated. This d del by dt we had calculated in terms of RPM. We got 20 RPM. And then this already directly omega Sm is the speed. So 120 F by P, which is directly in RPM. You don't need to find out that 2 pi ns by 60. Why? Because no need to convert it into radians per second. We need it in RPM only, which is equals to omega Sm. We need omega Sm in radians. In RPM. So you should not find out in 2 pi into ns by 60. The 2 pi into ns by 60 will give in the radians per second, but we need RPM. So we are finding the value of omega Sm. We found out this and we are getting this value by adding these two. Total speed. This is the speed, which is d theta m by dt. Now in this formula, we had used the swing equation, which is having h. Now how to solve a problem using swing equation, which is having m, where the del will be in mechanical radians. Let us see that. See here, a 50 hertz is the frequency. 4-pole machine, poles, number of poles is 4. Turbo alternator, directly this is MVA, you can highlight this MVA. So they had given SB base power, had inertia constant H, they had given the inertia constant. Now what they are asking, determine the kinetic energy stored in the rotor at synchronous speed. So they are asking for WK, first subdivision. So what is WK? We know the value of, they had given the frequency, they had given number of poles. This is not required. And they had given the base power. And okay, they had given H. They had given inertia constant H is 9. So I will write that. They had given that H is equal to 9 kilowatt second per kVA. Kilowatt second per kVA. So we know the value of H also per kVA. So you see this H is, we know that H is equals to WK into SB. In this, we know the value of SB and we know the value of H. So we can easily find the value of WK, which is H into SB, which is 9 into 20, 180 megajoules. Then we will read the remaining part of question. Determine acceleration. They had asked us the value of acceleration. If input power less than rotational losses is 25,000 HP. Unit is very, very important. They had given in HP. And the electrical power developed is 15,000. They had given mechanical power and electrical power. In the previous problem, they had given only electrical power. So, only mechanical power. So we had taken electrical power is 0. Electrical power is taken 0. You can observe here. See, electrical power is taken as 0. And when we are using this swing equation, this mechanical power and the electrical power are in per unit. When we are using a swing equation which has H, the mechanical and electrical powers are in per unit. So we had calculated the per unit mechanical power. But when we are using the swing equation which is having M, they are not in per unit. Very, very important. So you should not convert the mechanical and electrical powers into per unit when we are using this swing equation. These two are not in per unit. Not per unit. Why? Because see here, this per unit is due to division with SB. We had sent this SB to the other side and then only we got this M, right? See, this SB is not divided. This SB we are sending to the other side and this total term is represented by M. So there is no SB. So they are not in per unit. So very, very important thing. When we are using swing equation in terms of M, the mechanical and electrical power not in per unit. So you should remember this. Now let us go to the problem again. So they had given mechanical power and electrical power. Electrical power they had given in kilowatts, so it is no problem. But mechanical power they had given in HP. So you should remember 1 HP is equals to 0.735 megawatt. You should remember this conversion also. 1 HP is equal to, it will vary with the textbook. Some will be having 0.746. You can take any value. So 0.735 megawatt. You should remember this conversion form value. So I am taking the mechanical power and I am converting into megawatts, and they had given the electrical power, which is 15 megawatt or 15,000 kilowatt. Now, as I had already said, PM minus PE is PA, accelerating power. I had said there itself, which is equals to m d square d del square by dt square. That is, I am using a swing equation which is having this, which is equals to PM minus P. I am using swing equation which is having m. That is m d square del by dt square is equals to PM minus PE, which is equals to PA. So what is d square del by dt square? D square del by dt square will be, this is d square del by dt square. What is d square del by dt square? D square del by dt square will be PA divided by m. That is, PA is PM minus PE. So PM minus PE divided by m. PM is this 25,000 into 0.735, and PE is, this is minus 15,000 kilowatt. I'm taking both in kilowatts, divided by m. Now we should find the value of m. We had found out the value of WK in the first subdivision, which is H into SB. So what is the formula of m? M is equals to 2 into WK divided by omega SM. You can make use of this formula by, you know, the value of WK. So you can find WSM. This is one method of finding m. Another method of finding m is, you can substitute that omega SM is equals to 2 pi F naught, 2 gets cancelled. So directly you can take WK divided by pi into F naught. WK, how much we got? We got WK as 180 megajoules. So this is 180 divided by pi into 50, which is 1.146 megajoule second per radian. Now, okay, here you can take into 10 cube, 25,000 into 10 cube. Total I am taking in watts into 10.735. Here 15,000 into 10 cube. So total I am getting, this difference I am getting 3.375 into 10 power 6. That is, you can take this 10 cube, this 10 cube. Here this 10 cube and this 10 cube you can take common. So 25 into 0.735 minus 15 is 3.375. Now we got the value of m. So you can find d square del by dt square. When this is divided by this m, you got 2.945 radian per second square. This radian per second square is mechanical. Now you need to convert this radian per second square into electrical radians. Thereby you convert into electrical degrees. So I had explained you. So, okay, for now, this is acceleration. Acceleration A is equals to d square del by dt square. This is the second subdivision. We will proceed. We will see what they had asked. Then, if acceleration is computed is constant for 15 cycles, number of cycles is 15, determine change in torque angle in that period and the RPM. So they had asked change in torque angle in that period and RPM. So the same thing they had asked. In the previous, same like previous problem. In this problem, first subdivision, they had asked us to find WK. They had given H and SB. So we got it by finding H into SB. In second subdivision, they had asked us to find acceleration, which is d square del by dt square. t square del by dt square. And in the third subdivision, they had asked us to find power angle or torque angle, both are same, del, and speed in RPM. So now we had calculated d square del by dt square in radians per second, which is 2.945 radians per second. Now, if you integrate it 2 times, you will be getting the time is equals to, as I had said, time is equals to number of cycles by frequency. In the previous problem, there are 12 cycles and 60 is the frequency. So we got 12 by 60. In this problem, we had 15 cycles and 50 as the frequency. So it is 15 by 50, number of cycles divided by frequency. So you got the time period as 0.3 and del is 2.945 t square. T value is 0.3. 0.3 whole square divided by 2. We got this del in mechanical radians. You can understand this is mechanical radians. Now you should convert this into electrical radians and thereby you should convert this into electrical degrees. So actually, yeah, this is actually mechanical. So this is mechanical radians and this is electrical radians. So by multiplying this mechanical radians with 2 by p, let me change this there also. Yeah, this is electrical radians will be obtained by multiplying the mechanical radians by 2 by p. Now this electrical radians, electrical degrees is equal to 0.75 into electrical radians. So what we will get, one electrical radian, how you will get from mechanical radian into 2 by p, electrical radian into 57.3 will get you the electrical degrees. So this 2 by p into 57.3 into electrical. This is actually mechanical radian, sorry. See here, this is mechanical radian. This mechanical radian into 57.3 will give you the electrical radian. Electrical radian into 2 by p will give you the electrical degree. This total term will constitute the electrical degree. So now we had already what we had got. We got in mechanical radians. We got this here in mechanical radians. So you just multiply this. This is electrical radian. This is stick. This is also mechanical. This is mechanical radians. So you substitute this mechanical radians, what you have got here. This you can substitute here. This mechanical radians into 2 by p will give you the electrical radians. Electrical radians into 57.3 will give you the electrical degree. So we will get this term. And how to find this omega SMT? Omega SMT is 120 F by P. Here F is 150. This is 50. 120 F by P. This is the omega SM. And this is the total electrical degree. So you will by finding you will get 1500 or 1504.2 RPM. So the important thing is whenever you are having a problem where we need to use a swing equation in terms of m, you will get the del after double integrating the acceleration in radians. You need to convert that mechanical radians into electrical radians by multiplying with 2 by p. That electrical radians should be converted into electrical degrees by multiplying with 57.3. So this is the problems related to swing equation. Now let us see the problems related to equal area criteria. Now this is the circuit they had given equal area criteria. A 50 Hz, 60 Hz, this is the frequency, synchronous generator having inertia constant H they had given, and also direct axis transient reactance XD they had given 0.3 is connected to infinite bus bar through a reactive circuit. Okay, they had given this, and then they had given PE is equals to 0.8 per unit, Q is equals to 0.74 per unit, is connected to an infinite bus of voltage 1 per unit. Now, a temporary fault occurs at the sending end of the transmission line. What is that? At this point. First subdivision is at this point. This is A subdivision. When the fault is clear, both lines are intact. Determine the critical clearing angle and critical fault clearing time when the fault is at this subdivision, at this point. That is the first subdivision. Second subdivision is the fault is in the middle of one of the lines. There is a fault here at this middle. Here you had a fault. This is the second subdivision. When the fault is occurred at this point, then what we should do? We should find the value of critical clearing angle and critical clearing time. That is the second subdivision. Now let us see. Let me recall the formulas which are related to this equal area criteria. Equal area criteria works on the power angle or power angle equation. What is power angle equation? Power angle equation is PE is equal to P max into sin theta. This is the power angle equation. Now this P max is actually E dash into V. This is V. E dash into V divided by X1. This E dash formula, how to find this E dash formula is V plus J X1 into I. Now this V is voltage at infinite bus bar. That is voltage at infinite bus bar. That is they had given 1.0 per unit. So they had given this and they had given this diagram. Now we need to find out this E. E is equals to V plus Jx1 into I. We know what is the value of this V. V is the same thing, voltage at the infinite bus bar. Now we know we can find the value of X1. X1 is the equivalent resistance, equivalent reactance. You see here 0.3 plus 0.2 plus the parallel combination of these two. This 0.3, 0.2 in series, and this combination is in series with these two parallel combination. So what it will become, X1 is equal to 0.3 plus 0.2 plus 0.3 by 2, which is 0.65. Now how to find out this I? We need to find out this I. We know that S is equals to V into I conjugate. So that I conjugate will be S by V and I is equal to S conjugate by V conjugate. From this, I conjugate is equal to S by V. So I is equals to S conjugate by V conjugate. What is this S conjugate? S conjugate is normally what is S? S is equals to P plus J cube. So what is S conjugate? S conjugate will be P minus J cube. S is equal to P plus J cube So S conjugate will be P minus J. So they had given the P value and Q value in the problem. P is 0.8, Q is 0.074. So 0.8 minus 0.074 divided by V conjugate. V conjugate is 1 at an angle 0. So this is minus 0 or plus 0, no effect. So that is 0.8 minus J 0.074. Now we had obtained the value of I. We had found out the value of X1. We know the value of V. So we can find out the value of E dash. So E dash is equals to, this is V. This is the value of X1. And this is the value of I. So V plus J into X1 into I. So you will be getting the value of E dash. Now after getting the value of E dash, we should find the value of P max. This is P max. P max is equals to E dash into V by X1. We had found out the value of E dash, which is 1.17 is the magnitude. We need the magnitude alone. See, this is the magnitude into V is 1 divided by 0.65. So we got PE is equals to 1.8 sin del. This is PE. Now they had given the real power as 0.8. So you equate this to 0.8 and find the value of del naught. Del naught is equals to sine inverse of 0.8 by 1.8, which you will get as 26.388 degree. If you do in radian mode, you will be getting that as 0.46055 radians. Now this is del naught. Del max, this is the first subdivision. That is, first subdivision is fault is at sending end. Whenever fault is at sending end, this is the procedure you need to follow. Whenever fault is at sending end, you should first find the value of PE, which is equals to P max into sin del, where P max is E into V by X1, where E is V plus J into X1 into I, where I is equals to S conjugate by V conjugate. And then you equate this PE is equals to 1.8 sin del to the given power 0.8 and get the value of del naught. Now del max is equal to 180 minus del naught. This is the formula for. If you want to know how these formulas are came, you can refer the equal area criteria, transient stability equal area criteria derivation for first application. In derivation, we had discussed for two applications. First application is fault at sending end, and second application is fault at the middle of the transmission line. So you will be getting del max. Now the formula of critical clearing angle, del C is said to be critical clearing angle. So this is the formula for the first application. When the fault is at the sending end, this is the formula for finding the critical clearing angle. Critical clearing angle cos del C is equal to Pm by P max into del max minus del naught plus cos del max, where del max is equals to, just now we had found out, del max is equals to pi minus del naught. For these formulas valid only for fault at sending end. So you will be getting the value of cos del C. From that you can find the cos inverse of that. You will be getting critical clearing angle. Now critical fault clearing time. This is critical fault clearing angle del C. Now critical fault clearing time, you had a formula. This is the formula for critical fault clearing time, TC. In this TC is equals to 2H. H they had given in the problem into del C minus del naught by pi F naught into Pm. Pm is the mechanical power. We should equate, we are equating this is equals to Pm to find a del naught. No. At stable condition, Pm is equals to Pe, which is equals to 1.8 sin del. From that only we are getting this del naught. So that Pm is power given in the question. So you will get the critical clearing time. Now let us see the second subdivision. The fault is Actually, the given diagram is, this is the generator. Here we had a generator which is having 0.3. And then here we had a, let us see the given diagram first. Yeah. Here we had a transformer which is having 0.2. And then here we had a bus bar which is having 2 parallel lines. And the other end of bus bar is connected to infinite grid. Each parallel line is having 0.3. This is 0.3. Now in this subdivision, the fault is occurred at the middle. So when the fault is occurred at this point, the total is 0.3. So this will be 0.15. This will be 0.15. Similarly, this will be 0.15. So you can observe here, this 0.3 plus 0.2 together, I had written here as 0.5. And then this is 0.3. You can assume this as, here we had a 0.5 and then here we had a 0.5. This is 0.5. You should draw this diagram carefully. Why? Because when the fault is in the middle, we should go for 3 cases. You can see the graph of the derivation of the equal area criteria for the second application. When the fault is in the middle of transmission line, we will be having 3 cases. Before fault occurred, during fault occurred, after fault occurred, and we will be getting 3 swing curves. And here, sorry, this is 0.3. Here we had 0.15. This is 0.15. And this is also 0.15. Now the middle point of this is grounded. This is grounded, faulted, na grounded, no. So that's what I had drawn, 0.3, 0.5, 0.3. This is 0.15, this is 0.15. Now, when I am explaining the swing equation derivation, what I had transformed a star to delta. So now you should transform this star, this total star, to corresponding delta. The star should be converted to corresponding delta. So what will happen? You will be getting a delta like this. This is the delta which you will get, where this side is this 0.9. This combination of this 0.5 and 0.15, if you solve, you will be getting 0.9. And the combination of this 0.5 and 0.3, if you solve, you will be getting 1.8. And then this combination of 0.15 and 0.3, if you solve, you will be getting 0.54. Now, if you observe, this branch will be in parallel with this branch. See here, this is a line and this is a line. So I am redrawing the circuit. This is 0.9, this is 1.8, and this is actually 0.54. I am separating it. Anyhow, this is grounded, no? So I am separating it. Anyhow, it is grounded. So I am separating it. 0.54, which is parallel with 0.15. Now, the important thing is, before fault condition, we had already derived an expression. In the first application, whatever you have done, that is before fault condition. During fault condition, what is this? Normally, this equation can be written as P max sin del, where this P max is E dash. I had already found out the value of E dash, which I get as 1.17 into V modulus of E dash. Modulus of E dash into modulus of V divided by X is the max value. This X value will vary. This X value for before fault condition is the total X. We had found out, no. for before fault condition, this is total value that we had calculated before, which is 0.6765. You can see that. This 1.8 is obtained by dividing with that 0.65 only. Let me show you once again. See here. This is the total X value. This is total. Now, when we are having a fault in the middle of transmission line, we should go for 3 cases, during and after also. So the X value for during condition, it will be this value. You can see here, this value. This is the X value during condition, the X value. That is, we had a circuit like this. After star delta transformation, this is the delta which we had transformed, and this is the already existing parallel branch. This value should be taken as X for during condition. And then the X value for after condition, this E value, remaining all will remain the same. Only this X alone will change. For after condition, after fault, what will happen? The branch will be completely removed. That is, initially we had a generator here, and then we had a transformer here, and then we had 2 parallel lines like this. Here fault occurred, right? This is the fault point for this subdivision. So what you should do? You should remove this total part. You should be removed. This total part should be removed. It should not be considered. So what will happen for generator? The transient reactance is 0.3. Direct axis reactance is 0.3. For transformer, 0.2. And then for this upper line alone, this 0.3. So it will be 0.3 plus 0.2 plus 0.3. That is 0.8. You should only consider this value. This value alone. This is the value of X. This faulted line is removed. Here, this is 1.8. So you understood the value of how to take X before, during, and after fault. No, this is very important. If there is only fault at sending end, you can do the before fault alone, and you can use the formula of del max is equals to pi minus del naught, and you can find cos del C and TC. If the fault is in the middle of the transmission line, you should have 3 cases: before fault, during fault, and after fault. Before fault is a fault which had X is total value. During fault is this value. After star delta transformation, the value which is upside. After fault it is isolated. So remove that branch which is having fault and the remaining total value. So which is 0.8. So you will be getting 3 equations. I am taking PE1 is the power angle equation before fault, and then PE2 is the power angle equation during fault, and PE3 is the power angle equation after fault. This is PE3. This is after fault. Now, the formula for this del max, in the previous case 180 minus del naught, here the formula is 180 minus sine inverse of this 0.8 is PM, and this 1.4 is PE3 max. Remember carefully, this is PE3 max. So del max will be obtained by using this formula, 180 minus sine inverse of PM by PE3 max. You will get the value of del max, and cos del C formula for this application when there is a fault in the middle of the transmission line is this. We had derived this. You can refer the derivation. in the equal area criteria on video. In this, you can substitute and find the value of del C. This is the value of del C. And critical clearing time, you can use the same formula for critical clearing time. Critical clearing time formula remains same for both the applications. Since the del C changes for two applications, corresponding critical clearing time also will change. So you can substitute the value of del C, which is obtained, which you had got here in TC formula. You can find the critical clearing time TC, which is equals to. This critical clearing time formula is same for both applications. This formula remains same for both applications. Now, this is a problem on equal area criteria. Now, let us see how to solve the swing equation, obtaining the solution of swing equation using the three methods, that is step-by-step method, modified Euler method, and Runge-Kutta method. First thing is step-by-step method. In step-by-step method, first let us see what are the assumptions. The accelerating power PA is computed at the beginning of the interval is constant. PA is constant from the middle of preceding interval to the middle of the interval considered. Throughout any interval, the angular velocity is constant and the value computed for the middle of the interval. So here the formula is P average. First thing first formula is P average is equals to PA 0 minus plus PA 0 plus by 2. You should remember this formula. Then you have these three formulas. Del n is equals to del n minus 1 plus K into PA minus 1. And del n is equal to del n minus 1 plus del n. That is, you substitute here. This K value, you can take this. K value, you can substitute. K is equal to 180 F naught by H into del T square. So now you will get del n here. After getting del n, let me show you. Now this is the same problem which we had discussed in the previous case. But the only change is in this problem, okay, they had given a 50 hertz is the frequency. Unity power factor, okay, this is the value of H. They had given the value of H. And then they had given 1 per unit. Okay, V value is 1 per unit, V infinite. They had given del T is 0.05. Fault cleared in 0.4 seconds. They had given fault cleared time. Okay, now let us see the solution. The first step is for any of these three methods, that is step-by-step method or modified Euler method or Runge-Kutta method. First step is you should do the normal procedure of equal area criteria for a fault in the middle of the transmission line application. That is, at this point you had a fault. So you should find the value of pre-fault condition power angle equation, during fault condition power angle equation, after fault condition power angle equation. The procedure remains the same. So see, for pre-fault X is the total reactance. So 0.3 plus 0.3 by 2. And I am finding the value. Here in this problem, you no need to find E dash. They had directly given E dash. So you can directly find the PE. And if PM is not given in the problem, in the previous case, they had given PM is equals to 0.8. If PM is not given, you can take PE is equals to PM, which is equals to 1 per unit under steady state. So from this, you can find the value of del naught. This is the power angle equation for pre-fault condition. Similarly, during fault condition, like similar problem, you do the star delta transformation and you will be getting, you should take this as the X value and you got this is as PE2. That is the power angle equation for during fault condition. Similarly, you find for power angle equation for after fault condition. That is C. Here we had a generator. This generator is having 0.3. And then it is connected to a bus bar, which is having two parallel branches. And the other end is connected to infinite bus bar. infinite grid, infinite grid. Now this is 0.3. This is 0.3. Now fault is occurred here at this point in the middle. So for finding after fault condition, you just remove this value and you take only these two. So 0.3 plus 0.3, 0.6, you got the after fault condition also. Now, if you plot this already, I had explained how this graph will come. If you plot this, the peak value of normal condition before fault condition will be more than the after fault condition. The after fault condition will be, that is somewhat more than during fault condition. This is faulted condition. This is normal condition. Pre-fault. This is our pre-fault condition. Pre-fault will be more than post-fault than during fault. This is pre-fault condition. This is post-fault and this is during fault condition. Now we had did the normal problem. We had found out the three equations. Now let us move on to step-by-step method. First, PA 0 minus will be always 0 per unit. PA of 0 plus is actually 1 minus. What is this 0.875? If you observe, 0.875 is PE2 max. PE2 max sin del naught. Del naught we had obtained from PM divided by P1 max. How we had got this del naught? Del naught we got from PM divided, PM sin inverse of PM divided by PE1 max. From here, the problem starts. You apply sin inverse to this whole term. So now you got PA plus. This is the value of PA plus. Now you find the value of PA average, which is PA not 0 minus plus PA 0 plus by 2. Now this del n is equals to del n minus 1, as I had said, plus K PA comma n minus 1, and del n is equals to del n minus 1 plus del n. First we should find the value of K. K is equals to 180 F naught by H into del T square. They had given frequency is 50, H is 2.5 and del T is 0.05. So you will get the value of K. Now del n. What is this del n? Del n is equals to, in this formula, you substitute this K over here to get this equation. Del n is equals to, initially del n minus 1 will be 0. So del n is equals to K into PA of n minus 1. K is 9 into PA of n minus 1 is PA average. This PA of n minus 1 is PA average. So PA average is 0.2081. You will get the value of del n. Now after getting del n, sorry, this is the value of del n. Del n is equals to del n minus 1 plus del n. What is del n minus 1? That is del naught. Del naught we had already, this is the first iteration, no. So del 1 is equal to, you can tell that del 1 is equal to del naught plus del 1. Where this del 1, this is del naught. Del naught is 0. This is del 1. This is the first iteration. So del naught is 25.41 and del n is 1.872. So del n, that is del 1, is equal to 27.282 degrees. Now you had got del 1. Now you need to find del 2. This is del 2. Del 2 is equals to del n minus 1, which is del 1 plus k into PA1, k into PA1. Here we had got k into PA. This is PA0, PA0. How to find PA1? PA1 is same. Again, we had PA1 minus plus PA1 plus by 2. So, the same thing. 1 minus 0. This is again PE2 max. This is PE2 max. Now, since we are finding del 2, you should take the value of sine del 1. Previously, we are finding the value of del 1. So, you have taken the value of sine del 0. This is the only change. You have taken the value of del 0. Here, you should take the value of sine del 1. Del 1 is just what we had got. This is the del 1. So, now you will be getting del 2. And then del 2 is equals to del 2. Del 2 is equals to del 2 plus, what is the formula of del n? Del n is equals to del n plus del n minus 1. So, plus del 1. This is the value of del 1 and this is the value of del 2. So, you will be getting del 2. Now, if you want to find del 3, what is next third iteration, del 3, what you should do? Del 3 is equals to del 2 plus k into k value remains the same. PA 3 minus 2 is 2, PA2. What is this PA2? This PA2 is 1 minus PE2 max into sine del 2. Now you will get the value of del 3. After getting del 3, del 3 is equal to del 2 plus del 3. So you can take this del 2 value here and this del 2 value here to get the value of del 3. So this is the step-by-step method. Now let us move on to next type of problem, modified Euler method. In modified Euler method also, you can directly go to problems. We will understand it. You find out the value of these three equations. Then, now, we know that in the problem, if you see here, they had given PM. PM is 18 megawatt. And then they had given a base power, which is, this is SB. Since they had given in megawatt, what you should do? You should convert. Okay, here they had given 20 MVA base. So you should divide this 18 with the 20. You will get mechanical power is equals to 0.9. When we are finding del naught, what is del naught? Del naught is equals to sine inverse of PM by PE1 max. That PM should be in per unit. So if they had not given in per unit, you should convert it into per unit. In the previous problem, if you see, they had directly given in per unit. See here, we had found out, see here in this problem, 1 per unit. PM is 1 per unit. Even in equal area criteria problem we had solved, you can see there equal area criteria problem. See here 0.8 per unit. This is per unit. So whenever, very important thing is, when we are finding del naught, which is sine inverse of PM by PE1 max, the PM should be in per unit. That is very important thing. So this del naught is equal to sine inverse of PM in per unit, mechanical power in per unit divided by PE1 max. So you need to find the value of PM per unit, 0.9 we got, and then we had found out the value of del naught. In this modified Euler method, let me explain you the concept first. I think step-by-step method is clear. In step-by-step method, we had actually the formula for del n is equals to del n minus 1 plus k into PAN minus 1, where this del n is equal to del n minus 1 plus del n. So first thing is you should find the value of k. This is the first thing. And second thing is you can substitute the value of k here. The second thing is you need to find this PAN minus 1, that is this one. This is the second thing you should find. Then the third thing is this del n minus 1 for the first case, when we are finding del 1, this del 0 will be 0. You can remember that del 0 is 0. Similarly, PA of 0 minus will be 0. So now you will get del n after finding del n. This is the third step. Find the value of del n. And then you can substitute del n here. This is the fourth step. Now, I had shown for some iteration. For n is equals to 1, del 1 is equals to del naught plus k into PA comma 0. This del naught is 0. K is constant. This constant, how you will find? We had formula. What is the formula for K? 180 F naught by H. 180 F naught by H into del T square. This del PA comma 0 is actually P average, but in P average 0 minus term is 0. So you can directly take that as P of 0 plus, you can take it. So P of 0 plus will be, you remember carefully, this is PM, not 1 minus. In this problem, PM is 1. So you are taking 1. PM minus PE2 max sine del naught. This del naught is again, how to find out del naught, as I had just now told, sine inverse of PM per unit divided by PE1 max. Even this also in per unit. So you will be having del 1, you will get, you substitute this del 1 value here, and then you will be getting del naught plus del 1 will give you del 1. For second iteration, n is equal to 2, del 2 is equals to del 1 plus k into pa comma 1. This pa comma 1, how it will vary? Pm minus P2 max sin del 1. This del 1 what you have obtained here, this del 1 you should take, this del 1 should be taken here. This del 1 you had already calculated here, you can take that. And after finding del 2, you substitute this del 2 value here. Del 1 plus del 2 will give you the value of del 2. This is the procedure for step-by-step method. Now, similarly, let us understand this procedure for modified Euler method. Modified Euler method, we know del omega d del by dt is equals to del omega. We know that. So, initially, del omega naught will be is equals to 0. So what is del omega naught? Del omega naught is d del by dt, which is equals to 0. Then d square del by dt square can be written as d del omega by dt. So d del omega by dt is equal to, this is actually del omega. This is one formula you should remember. This is the second formula. That is the swing equation, nothing other than swing equation. D square del by dt square we had, no. We just, d square del by dt square can be written as d del omega by dt. So d del omega by dt is equal to pi by f naught into Pm minus Pe. That Pe we are taking Pe2 max sin del naught. The same thing. For first iteration, it is del naught. Second iteration, it is del 1. Third iteration, it is del 2, like that. Now, after finding this del omega naught and this 2, d del by dt and d del omega by dt, this is the formula. This is the third step you need to do. Del naught plus d del by dt at del omega naught into delta t. Similarly, del omega p1 is equals to del omega naught plus d del omega by dt into delta t. Now, after finding these two, del 1p and del omega 1p, you need to substitute here. Del 1c. You should find the value of del 1c and del omega 1c. You should remember this formula. This is the first formula, second, and this is the third formula. And then this is the fourth formula. This is the fifth formula. For solving a modified Euler problem, you should remember all these six formulas. Again, the same. Now we will see problem, you will understand. Initially, we will find P1 max, P2 max, P3 max. Now, first formula is del omega naught, which is equal to d del by dt at del omega naught, which is equal to 0. This is the first formula. Then the second formula, d del omega by dt, which is equals to pi f naught by h into Pm minus P2 max sin del naught. You got this. Then the third formula, del P1 is equal to del naught. This total term is del omega naught, which is 0. So this total is del omega naught, which is 0. And then into del t. Del t they will give in question. Then fourth formula, del omega 1p is equals to del omega naught plus. This we had already calculated. This total term we had already calculated in second. This is the first formula. You had calculated this in first formula. You have calculated this in second formula. You just remember the 6 formulas and proceed. That's it. See here. This is the first formula. And this is the second formula. We had obtained the value in second here. Now the next thing is, this is the next formula. You know the value of del naught, and this is the d del J by dt. This is first formula. This is first formula. And this what we had got here. This is third formula, right? This is the third formula. And this is the fourth formula. This value is actually the third formula. You can remember like this. This is the third formula into delta t. Similarly, this is the second formula. And this is the fourth formula. That's it, completed. Now let me show you the formulas and make it clear. See here. The first formula is this one. Del omega naught is equal to. Otherwise, simply you can write this as. The first formula is del omega naught is equal to del omega naught, which is d del by dt, which is equals to d del by dt. Then the second formula is, this is the first formula. The second formula is d del omega by dt. D del omega by dt formula we had obtained from the swing equation, which is equal to pi f naught by h pi f naught by h into P2 minus, sorry, PM minus PM in per unit minus P2 max into sin del naught. This is the second formula. Then the third formula is, this is the third formula. And then this is the fourth formula. Fifth formula is 1 plus 3 by 2 into del naught plus 1, del naught plus 1 plus 3 by 2 into del t. And the sixth formula is 2 plus 4 by 2. This is second equation, 2 plus, this is the fourth equation, 4 by 2 into del t. This is modified Euler method. Now, the next method is Runge-Kutta method. Runge-Kutta method also the same thing. Here we are taking as two functions. The first function is d del by d omega, d del by dt, which is equals to del omega, the same formula. The second function is d del omega by dt, which is equals to pi f naught by h into Pm minus P2 max. P2 max, this is P2 max into sin del. This is the second. This Pm is in per unit, as I had already told you. This Pm is per unit, and this del In the first iteration, it will be del naught, which is sine inverse of Pm per unit divided by PE1 max. Now, in this Runge-Kutta, we had second order and fourth order. Coming to second order, these are all the formulas we should be remembered. K1 is equals to F1 into del naught, comma, del omega naught del T. That is, what is this F1 del naught, comma, del omega naught? That is del omega naught, which is equals to 0. Then H1 is equals to F2 del naught, comma, del omega naught. That is, for this, what you should, for H1 calculation, here you should take sine del naught. Then K2 is equals to F1 plus F1 of del naught plus K1, comma, del omega naught plus H1 into T. We will understand this when we see problems. After finding K1, H1, K2, H2, this is the formula to find del 1. And for finding del omega 1, this is the formula. Similarly, for fourth order, we had K1, H1, K2, H2, K3, H3, K4, H4. And then we should find del naught, del omega, and then del 1 and del 2. Sorry, del 1 and omega 1 is equal to omega 1 is equal to omega naught plus del omega naught. Okay, now we will see a problem. The first step is we should find P1, P2. See, we found out P1, P2, and del naught we had found out. And then we had found out. The first step is, yeah, as I had told, this is the first step, which is equals to del naught, which is always 0. Then F2 is here. This is the equation. We are writing F2 is del F2 of del comma omega is d del omega by dt. This is the formula. Okay, now let us start with the second order Runge-Kutta. Second order Runge-Kutta, first K1 is equals to F1 of del naught comma del omega naught into delta t. What is this del naught comma del omega naught? This is actually del omega naught, which is 0. So 0 into 0.05. This del t will be given in the problem. Then H1 is equals to F2 of del naught comma del omega naught into delta t. How to find this? This is actually, you can substitute. This is the equation. In this equation, instead of this del, you take the value del naught. And this pi into 50 by h is giving 62.33. 0.9 minus 0.88 sine. This is the value of del naught. So you will be getting h. If you take this, you will be getting h1. Now, K2 is F1 of del naught plus K1, comma, del omega naught plus h1. That is, this is what is this? This is equal to del omega naught plus h1. Del omega naught is 0, so you will get only h1. What is h1? H1 is 1.7934, so 1.7934 you will get. Now, what is h2? H2 is F2 into del naught plus K1, comma, del omega naught plus h1. So, to find this F2, what you should do? You should substitute P max, Pm minus PE2 max F2, what is F2? F2 is this only, right? Pi by F0 into H. Okay, in front there is pi by pi F0 into H. Pi F0 by H. Pi F0 by H into Pm minus PE2 max sine. Instead of this del, you should take this term. Sine of del naught plus K1. If you solve for this, you will get the value of this function. This is the value of F2 into del T. So you will be getting this answer. Now you got K1, K2, H1, H2. Del naught is the average of K1 and K2. Del omega 1 is the average of H1 and H2. Del 1 is del naught plus del naught. Del naught is this, and del naught we had already calculated. Then similarly, omega 1 is equals to del omega 1 naught plus omega 1, omega naught, or the omega 1 you can take. So that is, del omega naught is 0. So the value of this del omega 1 is what we had calculated here. Now this is for second order Runge-Kutta. Similarly, we can solve for fourth order Runge-Kutta. For fourth order Runge-Kutta also, this function is equals to del omega naught, which is equal to 0. And then this function, you should take this del naught as the angle, that is pi f naught by h into Pm minus Pe2 max sin del naught. And then this K2 is del omega naught plus h1 by 2. That is, this value is h1 by 2. Why? Because this is 0. Now, h2 function, you should substitute in the place of del, you should take this angle. That is, pi by f naught into pi f naught by h into Pm minus Pe2 max sin of del naught plus K1 by 2. Then, similarly, you should find K3. K3 is F1. So, you will be having this term alone. You will be having this term alone. So, it is del omega naught is 0, no? So, it is h2 by 2. What is the value of h2? The value of h2 is just previous step, we had calculated the value of h2. So, the value of h2, you can see 1.7934. So, 1.7934 by 2. Now, h3. h3 now, this is f2. Wherever h, we will be getting the f2 function. That is d del omega by dt. That is pi f naught by h into Pm minus Pe2 max into sin del. Wherever we are having k, we will be getting the first function, which is d del by dt, which is del omega. So you should take the this value in that sine function. Then K4, again it is del omega naught plus H3, which is H3 1.7336 into 0.05. H4, we should take del naught plus K3 in the function. This F2 is actually, what is this F2? F2 is d del omega by dt. What is this d del omega by dt? This is equal to pi into f naught divided by h into Pm minus P2 max into sin del. This del value is variable here. Based on H1, H2, H0, H1, H2, H3, H4, this del value will be changing. This del value is changing. Similarly, what is F1? F1 is equals to d del by dt, which is equals to d del by dt, which is equals to del omega. This del omega is changing here. This is the unknown variable. Okay. Now we had found out the value of H1, H2, H3, H4, K1, K2, K3, K4. Now this is the formula to find del naught. And after finding del naught, del 1 is equals to del naught plus del naught. Similarly, This is the formula for finding del omega 1. After finding del omega 1 is equals to del omega naught plus del omega 1. This is the procedure for finding the solution of swing equation using step-by-step method, modified Euler method, and Runge-Kutta method. With this, the power system stability problems are ended. Thank you.